subtraction in fixed-bit binary using the 2's complement. This video will show you how to subtract in fixed-bit binary when the difference is non-negative. We need some terminology first. If we have x minus y equals z, the first number, x, is called the minuend. What we're subtracting is called the subtrahend, and the difference is z. We have a theorem that says subtraction in fixed-bit binary is accomplished by adding the 2's complement of the subtrahend to the minuend. But if the leading bit of the difference is 1, then there's another step. And I'll spill the beans and tell you that if the leading bit of the difference is 1, then that tells us that the difference is actually a negative number, and we have to decode that by taking the 2's complement of the difference yet again. But in this video, we're going to do the most simple case. We are going to compute the difference in 4-bit binary, but there's nothing sacrosanct about 4-bit. It could be any bit size, verifying that we really do get the correct answer when we add the 2's complement of the subtrahend to the minuend. Let's get started. Step 1. Let's encode 5 base 10 into binary. And it's 4-bit, because that's what we're doing in it. 4-bit binary. So this is actually really easy. I'm going to put 4 little squares for each bit. And remember, the leading bit doesn't have a place in the place value system. And we have 1, 2, 4. So if we encode 5 base 10 into this, we have 0 here, a 1 here, a 0 here, and a 1 here, because 1, 4 plus 1, 1 gives us 5. So this is 5 base 10. So step 1 is done, and that is relatively easy. Okay. So the next thing we're going to do, step 2, is we're going to encode 2 base 10 into binary. 4-bit binary, to be precise. 4-bit binary. I'm using ditto marks. These little, they look like quotation marks, but they're actually called ditto marks. I don't want to write 4-bit binary again, so I just do that. Now again, I'm going to put these little squares here to represent each bit, to remind myself that we are in exactly 4-bit binary. So the 2 is just 1, 0, and I'll put zeros in the remaining bits. And so that's step 2. Step 3 has actually 2 sub-steps, which maybe I'll call A and B. So what we need to do for step 3 is to get the 2's complement of the subtrahend. But in order to get the 2's complement, first we have to get the 1's complement of the subtrahend. So I'm going to call step 3A 1's complement of subtrahend. So what we need is we need the 1's, and the subtrahend here is this. This is the subtrahend, the 2 base 10. And so here, this is the subtrahend in binary. So I'm going to write subtrahend. Let me make sure it's in the frame. It is. Okay. So to get the 1's complement of this, we simply interchange the bits. So 1, 2, 3, 4 bits. And so we have 1, 1, 0, 1. So this is the ones complement of the subtrahend. Okay, so step 4, well actually step 3b, is to get the 2's complement of the subtrahend, which means we have to add 1 to the ones complement. So I like doing that. We're in 4-bit binary. I like putting a little bit box thing just to remind myself that I'm in 4 bits. This might not seem important now, but when we actually deal with the negative numbers, you'll see this. This will help tremendously to organize what we do. So let's do this. So let's write down the ones complement. It's 1, 1, 0, 1, 1, 1, 0, 1. And we have to add 1 to this. So here we're adding 1. And so 1 plus 1 is 0. Carry the 1. 1 plus 0 is 1. And 1 plus 0 is 1. And 1 plus 0 is 1. So what we have here is the 2's complement of the subtrahend. So we've completed step 3 in 2 steps. So now we want to verify that if we add the 2's complement of the subtrahend to the minuend, we will in fact get the answer that we are supposed to get. So let me move this up a little bit so it's in the frame perfectly. Okay, so let's do this and see what we have. So this is the 2's complement of the subtrahend, and this here is the minuend. I'm going to write this here. And I'm just going to write min for minuend. But this is the minuend. So step 4, I think I'll do step 4 on a separate piece of paper, just to make it a little easier. So step 4, we are going to add the 2's complement of the subtrahend to the minuend. Now remember, the minuend is 0, 1, 0, 0. And I think I'll put the little bit boxes in just to make it nice. Plus. So this here is the minuend. This here is the 2's complement of the subtrahend. And this should give us the correct answer in binary if this theorem works, and it does work. You'll see it does work, but that's the whole point of this. So here, the minuend is 0, 1, 0, 1. Let me make sure I'm in the frame. Yes, I am. And the 2's complement of the subtrahend is 1, 1, 1, 0. Now watch carefully what happens, because this is actually really, really cool that this works. So 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 0, carry the 1, and 1 plus 1 is 0. Now check this out. We're supposed to carry the 1, but we have nowhere to carry the 1 to because we are in 4-bit binary. Fixed bit binary, but in 4-bit binary. This will work with any bit size. But notice, the 1 that we are supposed to carry vanishes into oblivion, oblivion, oblivion. And it has to. See, if I proved this theorem for you, you would see this is a necessary condition for this to work. This must happen for this to work. Let me review what we just did. This is big time interesting. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1, and the 1 vanishes because we only have 4 bits. Now let's put the place values in and see what we have here. This is the 1's place. This is the 2's place. This is the 4's place, and this is the LB, the leading bit, which just tells us whether the difference is positive or negative. And so 2 plus 1 is 3. Now, if this theorem really worked, 5 minus 2 should give us 3. And it does. 2 plus 1 is 3. So we have shown that adding the minuend, adding the 2's complement of the subtrahend to the minuend does in fact give us the correct answer. So this is an application of this theorem, and I would prove this theorem to you if I get at least 5 comments asking me to prove it. But if I don't get at least 5 comments asking me to prove it, I'm going to let this go unproven. I hope you liked this video. If you did, maybe shoot me a comment at least, giving me some encouragement to make more of these types of videos. Have a great day.